Welcome to the course on Biostatistics and Design of Experiments. We will continue on this topic of design of experiments. We are going to talk about factorial designs today. So, I mentioned about two parameters, one is the drug, the other one is the diet. Okay. At two levels, drug has a level of no drug, okay, and same thing with the diet also has normal diet, high fat diet. So, we could conduct 4 experiments. The first experiment could be with the no drug and normal diet, okay. Then second experiment could be no drug and high fat diet, third experiment could be drug and normal diet, the fourth experiment could be drug and high fat diet. So, we have 2 parameters, 2 levels, 2 into 2, 4 experiments, you understand. So, by doing this we are achieving many things because we will be able to even see things like interactions. Is there an interaction between drug and diet? Is the person who is taking drug and high fat diet behaves very differently when compared to the normal diet or no drug, and so on actually. So, we also talked about what is interaction before. Let me recollect. Interaction is if 2 variables they behave in an additive fashion. For example, if I am looking at the product yield as a function of temperature and pH at a particular value of pH 3.5, as I change temperature or increase temperature, product may go up. So, at another pH again the product yield may go up. So, these 2 lines look almost parallel. So, the effect of temperature and pH on the yield is additive, whereas you can have situations like these, you know. So, at 3.5 pH product yield is going up, but at pH is equal to 4 it is going up with the less slope like this, or at pH is equal to 4 it may be going up with higher slope, unlike a parallel situation. So, then we can say the pH and temperature are interacting with each other in arriving at the product yield. Okay. So, the effect of temperature is not same at all pH values, but it depends on the pH values. Okay. For example, some drugs perform very differently with the Europeans as against Africans or Asians. Then you can say the drug and the race are interacting. So, if you want to study interactions, we need to definitely perform factorial type of experiments. That is very important. Okay. Then another important point which I had mentioned before is performing the blind and double blind test, because generally people will get influenced in a very unconscious manner, they will get biased. The medical practitioners, that is physician, as well as the volunteers or patients. Okay. So, if a patient is told he or she is being given a drug for treating their disease, or there could be some bias in the way they react. So, generally they are not told whether they are being given a placebo or a drug, that is a blind. But then even the medical practitioner or the clinician who is giving the drug may be biased when he or she is giving it to the patient. So, the doctor is also not told whether he is giving a drug or a placebo to the patient, who also does not know whether he or she is receiving a drug or a placebo. That is called a double blind. That is very important to do actually. Internal controls, this is very important to have. Okay. Sometimes we use the subject themselves as their own controls, right. Pair t test, for example, subjects themselves are used as a control. Sometimes especially when you are doing real time PCR, you all know in molecular biology we do quite a lot. We look at the housekeeping gene like actin, and then compare the performance, the upregulation or downregulation of rest of the gene with respect to the housekeeping gene. That is an internal control. Okay. So, it is very important that you also have a internal control in whatever you do, because that sort of normalizes the variations we see. Okay. Suppose I am doing an analysis with chromatography, I am looking at a particular peak, it may be changing, either it is going up or it is going down, but then if I have another peak which does not change, or which also changes, then I can take the measurements of the unknown with respect to the control. So, that sort of ratio is always better than dealing with absolute values. So, that way internal controls are very important. Okay. In many situations we always do that, especially biologists know very well where we use internal controls. Okay. Molecular biology, sometimes in biochemistry, product purification, chromatography and so on actually. Okay. Representativeness is very important, especially when you are doing a clinical trial. The subjects you are taking as volunteers, they should be representing the entire population rather than one strata of society. The tissue samples which you are taking, that should be representative of the population. Okay. You should generally study the material in a random population of interest rather than being only specific to one group of people. That is very dangerous. So, a characteristic of good experiments should be unbiased, that is randomized, blind, high precision, uniform material, same raw material, replication, blocking, simple, so that it will protect against mistakes, wide range of applicability. So, you change factorial designs, we are going to spend a lot of time on this. We should be able to estimate uncertainty, that is error. We should be able to get the confidence limits. How do you do that? We replicate, we calculate standard error, we have been spending a lot of time on all these actually. So, that is a measure of uncertainty. Okay, that is very important. Okay. Randomization is also very important if you want to bring in uncertainty, okay, rather than being very specific. Okay, let us look at some new terms. This is called critical to quality. We need to identify which parameters are very important, which are not. For example, in your product in a bioprocess product development, you can think of hundreds of parameters. Okay, carbon concentration, nitrogen concentration, various micronutrient concentration, the pH, the temperature, the agitator, RPM, the amount of oxygen you are bubbling, so many parameters, but only few of them will be very important. That is called the critical to quality. The goal is to identify only those few of them and focus and try to control them. That is very important. Okay. So, that is called critical to quality. So, you need to find what are the parameters which are critical to quality. So, when you do the design of experiments, initially you may take many variables and then you identify only few variables that are critical to quality. So, that type of experiment is called screening design. So, when you do a screening design, you take in many parameters and then you come down to only few 3, 4 which are critical to quality, and then you spend more time doing a very detailed design with that. So, generally we will do a screening design followed by a detailed design. Okay. For example, let us take the letter packets delivered by a courier company. Okay. And so, here delivery time is the most important parameter which one looks at actually, because the courier, even if you think about the pizza delivery, time taken to deliver is the most important. That is what everybody looks at, every customer looks at. So, what are the parameters that affect, what are the factors that affect? Maybe if he is driving a two-wheeler, airspeed, if he is driving a car, the age of the car, how well it is maintained, is it a working day or a holiday, how far you have to deliver, what is the driver's experience, how the neighborhood is it well laid out roads, what time, morning or afternoon or evening or night, average speed limit allowed, some roads allow 70 kilometers per hour, some roads allow only 25, 30, number of traffic signals, and then how many of them red at that point. Here we talk about snow or rain or any other factor, is there any road work going on the road. So, all these are going to affect your delivery time, right. So, many of them may be very important parameters, some of them are not very important, but you have large number of parameters which are to be at least initially considered if you are going to do a proper study. That is where we have something called a fishbone diagram. This is called a cause and effect diagram. Okay. It is a visual tool that enables us to identify, display, examine possible causes of variation. So, effect, this could be your product yield, this could be the time taken to deliver a pizza, okay. This could be amount of biomass produced. But what are the factors that affect here? Many things, you know, the type of raw materials you use, type of machinery, that means fermenter or bioreactor you use, and then type of people who are working on, how skilled or unskilled, what are the various techniques, the fermentation techniques you are using, what are the environment conditions, what are the measurement tools we use, so on. Lot of parameters will come into, and all of them will have some say in it. Some of them will have more say, some of them will have less say in the product yield, okay. This is called a fishbone diagram, and it is very useful because initially when you are planning your experiments, you can put down all the parameters. That is called a brainstorming. You put down as many parameters, complete whatever you think, and then we will be able to eliminate some of them, thinking that either they do not contribute much or their contribution is minimal. Thereby we can just focus on only a few of them, okay. So this fishbone is a good idea to prepare, especially when you are planning a DOE. So before you do a DOE, you can use this, but of course in a bioprocess fermentation, we all know what are the parameters that is going to affect. But if you take a much more complex process like a manufacture of a biosensor, there could be raw material related, there could be manufacturing related issues, there could be type of instrument used, and so on. Or if you take a clinical trial study and you want to look at some effect, that is very complicated. If you are talking about clinical trials, you have doctors, medical practitioners coming into picture, you have nurses coming into picture, you have the volunteers coming into picture, the type of drug, the type of assays, the different type of analytical tools used, all these come into picture. It is extremely complex. We can put down as a pictorial form a cause and effect diagram. This is called a fishbone diagram because this looks like a fishbone, okay. And some of the parameters may not be in your control at all, some of them may be in your control. For example, if you take your pizza delivery, the road work, you have no control. If there is a heavy rain or heavy snow, you have no control, okay. The number of red lights coming on the way, you have no control, but you have control like the driver's experience, the car's quality, all these you have control, right, okay. So there are some factors which you do not have control and some you have control. Okay, so initially you do something called a screening design. So you eliminate less important factors and the remaining factors are called key factors. Then you do a detailed design, you have linear design, second order designs, so that you can fit a linear or non-linear type of regression mathematical equation, okay. So you have factors which are key factors which you have shortlisted from the entire set of factors using a screening design. Okay. Another important parameter you need to consider is operability versus region of interest. For example, if you take pH versus enzyme activity, generally you all know it is a bell shaped curve or it is a curve going up and coming down and so on. Okay. So at different pHs the activity may vary, but if you are operating at only a very short range of pH like 3.5 to 4, this looks almost linear and we can say the enzyme activity does not change with pH, but in reality it changes, which is the region of operability. You can operate at any time, but if you are interested only in a very narrow range, then obviously the enzyme activity does not change in that particular narrow range. So it depends on which regions you want to study. So temperature will affect your reaction rate, conversion process, but then if you think I can work only between 35 and 40 degrees, then that range of temperature will not have any effect on your activity. But in reality, if you work at a very large region of operability for temperature, then definitely the activity will vary with temperature. So it depends on the region of operability and the region of interest, okay. So, in the region of interest in which you are studying, that particular parameter will not have any effect on the activity. You need to keep that in mind. Okay. As I said, there are some parameters which you do not have any control, there are some parameters which you have control. The parameters which you do not have control, like the traffic lights or the road work that is going on or heavy rains. So, they are called the key noise parameters. The parameters which you have control or the key control parameters, that means temperature I can change, temperature in a fermenter I can change. Okay. So, for example, environmental factors, the humidity conditions, the ambient temperature, in a bioprocess you have no control. Okay. The volunteers' health change during drug trials. You have started a drug trial and sometimes the drug trial will last for 2 months, 3 months, and then suddenly the volunteer may get a fever. You have no control, right. That is called the key noise parameters. Key control parameters you can exactly control. Okay. In a fermenter, temperature, pH, I can exact amount of nutrient added, amount of micronutrient added, you have exact control on that actually. Okay. So, that is called the key control parameters, and that is what is very important. Noise parameters we have no control on it actually. Okay. So, originally I said we can change one factor at a time and do a study, that is called the one factor at a time study, that is varying one factor at a time. For example, I am looking at temperature, I vary temperature from 30 to 40 degrees in steps of 2. Later on I take pH, I vary pH from say pH 4 to pH 7 in steps of 0.2. So, that is called a one factor at a time design, that is not a factorial design. Okay. If when you do that, you will not be able to see interaction. So, if I have pH and temperature and I first study only pH effect, later on I will study only temperature effect, then that is called a one factor at a time design. I will not be able to see interaction between temperature and pH, whereas if I change both temperature and pH in a factorial way, then I will be able to see the interactions. Okay. Number 1. Another thing is, when you are doing one factor at a time design, it may be more difficult to arrive at the optimum condition as against changing many factors at this time simultaneously. Okay. So, one factor at a time design is extremely not correct to adopt. So, please remember, next time you are running a fermenter and you want to change temperature and pH, it is very bad to just change temperature at 5 different values, look at the results, then change pH at 5 different values and look at the results. That is very bad and very inefficient. You will not be able to see the interaction effect. So, the best thing is to go for some sort of a factorial design where you change temperature and pH in a very simultaneously, in a very well planned out design strategy. There you can see the effect of both temperature and pH individually as well as when they are interacting. So, in future always use some sort of a factorial design methodology if you want to change more than one factor. Okay. So, the one factor at a time design is completely wrong. Okay. So, let us look at a factorial design experiment. Imagine I want to change like in the previous example I said drug, no drug, okay, that is called 2 levels, then diet, normal diet and high fat diet, that is based on diet 2 levels. So, I have 2 parameters, one is drug, one is diet, and each of them at 2 levels, that is called a 2 into 2, 2 raised to the power 2 design. So, if I have 2 factors A and B at 2 levels, then I will call it 2 raised to the power 2 design. So, this 2, the bottom 2 is an indication of the number of levels, that means diet and high fat diet, that is the level, no, and this 2 tells you how many factors or parameters I am running. So, if I have 3 factors A, B, C, then I will call it 2 raised to the power 3 design, understand, that is 2 into 2 into 2, 8 experiments. If I have 4 factors A, B, C, D, that means temperature, pH, carbon, nitrogen, 4 factors, each one I am studying at 2 levels, then it will be 2 raised to the power 4 design, 2 levels. Okay. People does study at 3 levels also, but let us look at 2 level design as of now. So, I am temperature, pH, carbon, nitrogen, these two at different concentrations, each one at 2 levels. Okay. So, the temperature could be at 30 and 40, pH could be at say 4 pH and 5 pH, carbon concentration could be 1% and 2%, nitrogen could be 0.5 and 1%. So, 2 levels. So, that is a 2 raised to the power 4 design, that means 2 into 2 into 2 into 2, 16 experiments. That is called a factorial design. Factorial designs are very efficient. It will also give averaged effects without the need for replication. It can also look at interactions, because as I said, we are going to change many variables at the same time. It gives you a nice idea later on to optimize. Ultimately, I want to optimize my process. Okay. Okay, now let us look at this 2 factors A, B at 2 levels. So, 4 experiments. So, how do I do the 4 experiments? I will keep A at low, B at low, then I will change A at high, B at low, then I will change A at low, B at high, then I will change A at high, B at high. So, I have done 4 experiments, and both the factors have been looked at low level and high level. And as you can see, in some cases I am changing both the factors so that I can even look at interactions here. So, that is the beauty of this type of factorial design. Okay. It is extremely powerful. So, 2 raised to the power 2, 4 runs I need to form. So, the first experiment I will suppose this is temperature and pH. Okay, if this is temperature and pH, and the temperature is 30 degrees and 40 degrees, 2 levels I want to study, pH I want to study at 3 and 4 pH. So, what do? The first experiment will be 30 degrees temperature and pH 3. Second experiment will be 40 degrees temperature and pH 3. The third experiment will be 30 degrees temperature and 4 pH. The fourth experiment will be 40 degrees temperature and 4 pH. Okay. So, I achieved all the 4 in different combinations. Do you understand? Okay. So, the low means the lower level for A we have chosen, in this case 30 degrees temperature. High means higher level for A we have chosen, 40 degrees temperature. Low for pH means say pH 3, high for pH means pH 4. Okay. So, that is how you do these experiments. Okay. Understand? Okay. So, you have a 2 level, 2 factors or 2 parameters, that gives you 4 runs. So, you can have 2 raised to the power 3 design, 2 power 4 design, 2 power 5, as you keep on increasing the parameters or factors actually. So, if I know the I am looking at say time and temperature, and I am getting the yield here. Okay. So, what do? What will be the effect of time, for example? I have done say experiment 1 and 3 makes use of time at 80, and experiment 2 and 4 makes use of time at 90. Okay. So, what I do? I add these 2 results, divide by 2, then I add these 2 results, divide by 2, subtract one from another, that will give you the effect of time. Do you understand? Because time is done, there are 2 experiments where you have done at 80, there are 2 experiments where I have done at 90. So, what do? The results of, you take 46.2, 79.5 minus 2 minus 58.3 plus 47.7 by 2. This is the effect of time. The yield has changed, increased by 9.85 because of the change in time from level 1 to that is 80 to 90. Now, look at temperature. These 2 experiments are done at lower temperature 170, these 2 are done at higher temperature 180. So, you add up these 2 results, divide by 2, add up these 2 results, divide by 2, and then subtract this from that. So, 47.7 plus 79.5 by 2 minus 58.3 plus 46.2 by 2 gives you 11.35. That means, increasing temperature by 10 degrees is increasing my yield by 11.35. Increasing the time from 80 to 90 increases my yield by 9.85. Okay. So, it is extremely powerful, we can analyze the results, and we can get the effect of main parameters, we can even get the effect of interactions also. I will talk about it later, okay. We will look at that also in due course, but this is a very good experiment. It is a 2 raised to the power 2 design, and the bottom 2 indicates the levels, this 2, the top 2 indicates the number of factors or parameters we have. So, we can have different types of designs, and we will spend more time as we go along, and next will be the full factorial designs. Okay. Thank you very much for your time.